All right, next up we have a bit of review once again, calorimetry. And so our next experiment involves the use of a calorimeter again. So I want to review calorimetry. So here's how it works. Energy is transferred to an unknown substance from water or from an unknown substance to water, just depending on if it's an endothermic or exothermic process that's occurring in the water. It's always in water. This occurs in a well-insulated container, so no energy escapes to or comes from the surroundings. The important part here is the amount of energy change that the water undergoes is the amount of energy change that the unknown or the system must have undergone. So just a reminder, a calorimeter is a well-insulated container that contains water where a transfer of energy between the water and something occurs. There's some background information way back, pages 64 to 69. We're going to be using, again, Q equals MCAT for these calculations. Anytime a substance's temperature, such as water, is changing, we can use Q equals MCAT to calculate the change in energy that occurs. So let's take a look at this example. It says, suppose that 100 grams of water at 22.4 degrees Celsius is placed in a calorimeter. A 75.24 gram sample of aluminum is removed from boiling water at a temperature of 99.3 degrees Celsius and quickly placed in the calorimeter, just like the specific heat lab we did earlier in the year. The substance, and really should say substances, reaches a final temperature of 32.9 degrees Celsius. So this is the temperature of both the water and the aluminum. Remember, we reach thermal equilibrium where both substances have the same final temperature. Determine the specific heat of the aluminum. Now, you can separate this into two steps where you first find the energy gained by the water. Notice the temperature of the water is going up, so it is gaining energy. Use Q equals MCAP for that, and then set that Q equal to Q equals MCAP for the metal and solve for C. I'm going to set it up once again in one step. So let me write something out here for you first. So remember, Q for the metal is equal to Q of the water. Technically, it's negative Q of the metal is equal to Q of the water, just for our sign conventions. Technically, it's TF minus TI, and the initial temperature of the aluminum is greater than the final temperature, and so we'd get a negative Q for aluminum. So we'll just do delta T, absolute value of delta T in both cases here, and then we can ignore this negative. So we'll just write it like that. And so we have MCAT of the aluminum is equal to MCAT of the water. And if you want to label that with Al, 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 H2O, 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 that's fine. And so what we're looking for is the specific heat of the metal. And so I'm going to rewrite the equation. So we have MCAT for the water. Make sure you know which values go in which place on our setup, over mass of the metal. And so the mass of the water was 100.00 grams. Sometimes we're given the volume of water, and if we're given the volume, then we can just use the density to find the mass. So 100 grams. Anybody remember the specific heat? Let's see, specific heat of water. We'll go 3 sig figs, 4.18 joules per gram degrees Celsius. And then the change in temperature of the water, I'm just going to plug in that number here. We can do two things. We can plug in the initial and final temperature if you want. But I'm going to go ahead and calculate that and then plug that in. So let's do that. So the change in temperature, be careful of your sig figs, is 10.5 degrees Celsius. That's the change in temperature of the water, divided by the mass of the aluminum, which is 75.24 grams. Times its change in temperature. And once again, I'm going to calculate that and then plug that number in. So let's do that. So the change in temperature of the aluminum is 66.4 degrees Celsius. Take a look at our units here. Grams cancels, degrees Celsius cancels, we're left with joules per gram degree Celsius, which is an appropriate unit for what we're trying to find, which is specific heat of the metal. Go ahead and pause the video and punch it up, see what you get. And you should get 0.879 joules per gram degree Celsius. All right, go ahead and give this one a try. Again, we're looking for specific heat. Go ahead and pause and set it up. Don't really care too much about the 2 sig figs in our masses here. That really limits our precision of our answer, but nevertheless, we get 0.86 joules per gram degree Celsius. All right, I have another example for you to work on. I think you have a blank page in the back of your note packet. So let's take a look at this one. Let's add number 3. It says 1.10 grams of sodium hydroxide, which is a solid, is added to 100 milliliters of water at 22.0 degrees Celsius. Once all the solid has dissolved, the temperature of the water is found to be 25.2 degrees Celsius. First of all, is the dissolving of sodium hydroxide endothermic or exothermic? Well, is the sodium hydroxide as it dissolves absorbing energy from the water being kind of the surroundings here, or is it releasing energy to the water? How we determine this is we look at the temperature, final and initial temperature of water. It looks like the water is heating up. Well, that means that the water is absorbing energy. Where is it getting this energy from? It's getting it from the dissolving process. So this process is exothermic. All right, so next up, let's calculate something called heat of solution. So the delta H for this process. Now, it should be noted that delta H has units of kilojoules per mole. Total amounts of energy absorbed or released in kilojoules per mole of the substance that is undergoing the change. Now, this one's a little bit different than the last 2 examples. In the last 2 examples, the metal really didn't interact with the water in terms of its changing because of being placed in the water. You just have it set in the water, it's releasing energy to the water, and that's it. In this case, we have the chemical actually interacting with the water. It's dissolving in the water. And so technically our system is the water and the sodium hydroxide. And so that has implications for our calculation, as we'll see in just a second. So let's go ahead and set this up. Once again, we want to calculate the amount of energy gained by the, I'm going to say solution here. And to do that, we're going to use Q equals MCATs. We have 100 milliliters of water. Density of water is 1 gram per milliliter, so that gives us 100 grams. However, we're dissolving 1.10 grams of some other substance in water, so technically our total mass is the sum of the water and the sodium hydroxide. So we're going to have a total mass of 101 grams. So this is water and sodium hydroxide. Very important for this type of calculation. We'll assume that the specific heat of this solution, which is almost entirely water, is the same as water by itself. Our change in temperature is 3.2 degrees Celsius. Go ahead and pause and punch that up and see what you get, and then I'll show you how to finish this problem. Kind of has some weird numbers here, 1350.976, so I guess we'll go 1400 if we want to go 2 sig figs. Again, not too happy about the lack of precision here, but that's okay. So either 1300, 1400. This is a little bit closer to 1400 than it is 1300, so we'll go with that. So now remember, we're trying to find heat of solution, which has units of kilojoules per mole. So we want the total energy in kilojoules, which is 1.4. And we're going to take that and divide it by moles of whatever is dissolving. Now, again, we can do this as a separate step, or we can just write that here. So this time I'm going to combine steps. And so I want to convert from grams of sodium hydroxide to moles of sodium hydroxide on the bottom. Molar mass happens to be 40 grams per mole. Remember, this process is exothermic, so be careful about how you give your answer. Go ahead and pause and see what you get. So once again, we want our answer to 2 sig figs. So this is what you get in your calculator. Going back here, this process is exothermic. Do you remember anything about delta H for an exothermic process? That's right. We have to put a negative in front of that number. So the heat of solution of sodium hydroxide is negative 51 kilojoules per mole. This will be a very important calculation for our lab where we're calculating heat of solution if a substance is dissolving or reacting with our solution. We want to calculate heat of solution, energy absorbed or released when a substance dissolves. All right, that concludes part 1 of this lesson. Part 2 will be on something totally different. I just want to make a separate video with Hess's law, and we'll learn how to calculate, once again, delta H for some chemical reaction. Thanks for watching.